Hey, I'm Mitchell and welcome to another video in the RSP education series. Ever wondered why some industrial machines drain power like crazy while others barely make a dent in your energy bill? It all comes down to watts, how much power is actually being used, but here's the catch. In AC systems, not all power is created equal. Stick around to learn the difference between real, apparent, and reactive power, why understanding watts is critical for optimizing your industrial automation setup. If you like this kind of content and want more educational videos, please like and subscribe. Also, this video is for educational purposes only. Consult a professional for your applications always. RSP Supply is not liable for any misuse of this information. With that said, let's get right into it. Before we dive too deep into watts, let's quickly recap voltage and amperage, two key electrical elements that directly impact power. So we discussed these two already. Voltage is the electrical pressure that pushes current through a circuit. Amperage is the flow of electrical current, or how much electricity is moving actually. Now watts. Watts are going to measure electrical power, which tells us how much energy is being used or produced per second in an electrical system. The basic formula is watts equals volts times amps. In DC systems, power, or watts, is simply, like we said, the product of voltage times current. It's straightforward because DC power flow is constant. It doesn't fluctuate. A good example, let's say you have a light bulb that runs on 120 volts and uses 2 amps of current. This is going to consume 240 watts when it's on. More voltage or more current means more power or more watts. In AC systems, power is a bit more complex because of the power factor. AC power has voltage and current that may not always be in sync due to reactive loads like motors and transformers. In AC power, watts equals voltage times current times power factor. So the power factor is going to represent how efficiently the system converts electrical power into usable work. Now let's understand a little better energy consumption. So watts measure power, but energy consumption is measured in watt hours or kilowatt hours, kWh. A kilowatt hour is a way to measure how much energy is used over time. The kilowatt represents the power level at a given moment. The hour represents the time that the power is used. Power times time equals kilowatt hour, kWh, or total energy consumed. Some examples. Let's say we have a 100 kilowatt motor running a conveyor belt for 5 hours. So 100 kilowatts for 5 hours or times 5 hours equals 500 kilowatt hours. If that same motor runs for 10 hours, that's a 100 kilowatt motor times 10 hours. We've consumed 1,000 kilowatt hours or 1 megawatt hour. Measuring power is critical in industrial automation to identify energy-hungry equipment and implement energy-saving strategies. Detect anomalies such as excessive power draw, phase imbalances, or inefficiencies. Understanding power in industrial automation. So watts measure power, or the rate at which electrical energy is used or produced. Let's break down the 3 key types of power. We've discussed these before, but it doesn't hurt to review. Real power, apparent power, and reactive power. Real power, that's kilowatts, remember? That's the actual usable power, the power that actually performs useful work, like running PLCs, powering motors, actuating solenoids, or energizing relays. For example, a servo motor in a robotic arm may consume 5 kilowatts. That means that that's the actual power used to move and control the system. Apparent power, or kVA, that stands for kilovolt amperes, that's the total power drawn, or the total power supplied to a circuit. The total power supplied to a circuit including both usable and wasted power. It's usually measured, like I said, in kilovolt amperes, kVA. An example would be a VFD, a variable frequency drive in an industrial conveyor system. It may be drawing 8 kilovolt amperes, 8 kVA, but only 6.5 kilowatts is actually being used for motor operation. The rest is due to inefficiencies. Lastly, we have reactive power, or kVAR. That's the unused power in the system. This is power wasted in inductive or capacitive loads. It's usually measured in kilovolt amperes, reactive, kVAR. This is the power that does not perform useful work, but it still circulates in the system due to the inductive nature of industrial automation loads, like motors, transformers, solenoids, and other relays that establish magnetic fields. Although it's not performing actual work like real power measured in kilowatts does, reactive power is still crucial and necessary for the stability and efficiency of AC power systems. Devices like motors and generators and transformers rely on reactive power to create their required electromagnetic fields, like I said. Without reactive power, these devices would not function properly, leading to inefficiency and potential damage. Even though reactive power doesn't translate directly into work, it's still essential for the overall functioning of the power system. So now you know, watts are more than just a number on a spec sheet. They define how efficiently your industrial systems run, and understanding them can save you serious money and prevent costly downtime. But here's the real game changer: power factor correction. Did you know a poor power factor can lead to utility penalties and unnecessary strain on your equipment? In our next video, we'll dive deeper into why power factor matters involving watts and how it impacts industrial automation, how you can fix it with the right solutions. For hundreds of thousands of other industrial automation products, go to our website. For any other information or more educational videos, go to rspsupply.com, the internet's top source for industrial hardware.